In this video, we're going to continue looking at the mathematics behind oscillations. So let's consider what's happening with the system. We're going to look again at, for instance, the Io moon going around Jupiter. And we're not going to ask just what's its position doing. We can look up in the sky and see what's happening, but let's start looking at the mathematics behind the velocity of acceleration. This is what we did at the very beginning of Physics 1, so let's continue that practice. So we know that the equation of oscillation for Io, as we plotted it, is a cosine function. It starts off with a maximum amplitude, and as time progresses, the period of oscillation, this angular frequency in this case, will determine what it looks like. So we start off at a maximum, go down to the most left, and then go back up to the most right. We oscillate back and forth. So this is my position versus time graph for just a little over one oscillation. So I start here, go to one oscillation, and then go a little bit further. So now we're going to ask what's happening to the velocity. And the velocity is based off of the derivative of the position versus time. And if we don't remember calculus, we don't want to get freaked out about it. We're not going to do that. We're not going to let that happen because we're smart enough to know that all I'm saying when I say derivative is just meaning that the slope of the line, slope of this graph at any point, is going to give us what we're going to get down to here. So let's start stepping through some of these. When we're at the very top, we see up here we have a slope of 0, right? It's at the maximum amplitude, it's coming up, and then it's decreasing. So at here, it has no slope. It's a slope of 0. So we're going to put a point down at 0. Move a little bit over, we see that the slope down here, the tangent line here, has a negative slope. So it's going to be a little bit of a negative slope. It's a negative value. Here, it gets a little bit steeper, so we're going to put a little bit of a lower value. Again, a little bit steeper, it's going to be a little bit lower value. Finally, when we get here, at this point, it has a slope. This is going to be its maximum slope, maximum in a negative value. So we're going to put a maximum slope here. It's going to have a point. And continue on. Again, the slope is getting a little bit less. It's steep there. It's getting a little bit less steep. As you see, we're at the very bottom. We start to flatten out again, so we're back to 0. Now, here we see we have an increasing slope that's going to then go back to 0. So we increase, increase, increase. We're now at the maximum slope. So we keep going through, and we finally get back to the original position. If we look at what happens at v as a function of time, we can just take the mathematical function, which we'll call a derivative, and find it. And we find that this is the equation for it. We saw that this is the minus sign curve. So we'll find that the amplitude that this thing has an amplitude, an absolute value of the amplitude of a times our angular frequency, or a omega. But we added this minus sign in, and we get this sine function showing up. So we now are oscillating between a omega and minus a omega, so we know its maximum and minimum velocities, and we can see as a function of time what's happening. Is it turning around? Is it going back? What direction does it have its velocity pointing? We can do this again, and we know that the slope of this line is the slope of the velocity versus time graph at any point is going to be the acceleration. And mathematically, we can just work this out. We take the sine, it gets turned into cosine. This is partially just because we're taking a derivative, and we get an extra omega squared from this. We keep the same minus sign because here we start with a negative slope. So if we look at it, we start with a negative value here. And as the slope gets less and less and less, here it goes to 0. So we go there. At this point, we get positive, so we're starting a positive slope. All these points match up again. I'm not going to go through everything one by one like we did for the velocity, but you get the point. Well, if we actually look at this, we can start thinking of combinations of these three equations in an interesting way. So again, we have our three equations, position as a function of time, our velocity as a function of time, and our acceleration as a function of time. And we notice something interesting. We notice that the position, this a cosine omega t minus phi, shows up here. A cosine omega t minus phi. So that's exactly the same thing. So if we go back through, we can see that that just goes in, substitutes out, and we can just replace this by position. Just a simple substitution. We have to take into account this negative sign here and the omega squared. So we get that to show up here. So when we see this, we get this wonderful equation that says the acceleration is related to the position, and the factor that's related by is the minus of the angular frequency squared. So if we can find something, this is just our equations for general oscillations. So if we can ever find a system that holds to this one, we saw with Jupiter that this is going to happen for this. We modeled our mathematics off of the thing. But if we can find something that has a physics that holds up to this equation, we can then use these results later on. And that's actually what we're going to do with a lot of different systems, is every one of these systems is going to have the same general thing where we have the acceleration, which is the slope of the position. So if the slope of the position, or the second derivative as a function of time, is related to the opposite of the position itself, then we get what's called harmonic oscillation, or just general simple harmonic oscillators. So all these are going to show up multiple times, and we're going to see at least 2 different times, but in physics these show up many, many, many times. So we call this the harmonic oscillator, simple harmonic motion, periodic motion. All of these things that are represented by a cosine or a sine function will have this ability, and that's why we're going to group them all together. So we're going to keep going through this. We're going to look at an example in the next video of a spring mass system that actually has this property.